The title of today's experiment is Hydrogen Evolution Kinetics Dependence of Material. The objective of today's experiment will be to understand what is overpotential, to find out the exchange current density, and to plot the Stafford plot. These two will be used to determine the material of the electrode. So in this experiment you will be given two electrodes, one will be platinum and one will be silver. So you will have to conduct few experiments to determine which is the platinum electrode and which is the silver electrode. So to start with, what is overpotential? We will be using hydrogen evolution kinetics or the hydrogen evolution reaction to determine the material of the electrode. So at standard temperature and pressure at 0 pH, when we apply 0 volt with respect to standard hydrogen electrode, the hydrogen gas will start evolving on the electrode. Okay. But for now we don't have standard hydrogen electrode, we are having saturated calamine electrode whose standard potential is 0.24 volts. So on this scale it is somewhere around over here. If I shift the origin from here to here, let us shift the origin, let's make this as 0 volt. So the hydrogen evolution will happen at negative 0.24 volts. Okay, this will be with respect to saturated calamine electrode. When you apply negative 0.24 volts with respect to saturated calamine electrode, the hydrogen gas will start evolving. But the place where we are conducting the experiment, the temperature is not standard. Also, the electrolyte that is given to you is not 0 pH. So to consider the effect of temperature and the pH, we will be using Nernst equation to find the equilibrium potential. So when you put in the temperature and the pH of the electrolyte into this Nernst equation, you will get an equilibrium potential, and it will be somewhere more than the actual hydrogen evolution voltage. So this is the equilibrium potential. When you will apply the equilibrium potential on the electrode, still the hydrogen evolution will not begin because we have not considered the effect of material on the electrode. So basically what happens is the material should have an optimum bond energy, bond strength with the hydrogen molecule that is being evolved on its surface. If it should be strong enough to hold the intermediate species of hydrogen gas, and also it should be weak enough to let the hydrogen evolve away from the electrode surface. So basically platinum is having a optimum bond energy with the hydrogen, so it will be having less overpotential, as well as it will be having more exchange current density. Okay, so when we consider the effect of material, we will have to apply even more voltage than the equilibrium potential. So at this point, this is the point wherein the actual hydrogen gas will start evolving. The first molecule of hydrogen will evolve at this point. So this is called as the onset potential. Okay, so at this point the hydrogen gas will start evolving. On the y-axis it is the current density measured in amperes per centimeter square. The more and more voltage that you apply, you will see that the current density will keep on increasing. The current density indicates the amount of hydrogen gas that is being evolved. Okay, so any voltage above the equilibrium potential, this is the overpotential. Okay, anything above it is the overpotential. This. Okay, so the equation is to find the overpotential, the voltage applied. So this is basically the voltage applied. This is the voltage applied minus the Nernst or the equilibrium potential. Okay, so if you minus this part, you will get only this value, which is the work. Thank you. The second objective of this experiment is to find the exchange current density. So you will have to perform a linear polarization on the potential side to find out the exchange current density of the material. To begin with, what is exchange current density? We have an electrode dipped into an electrolyte. So at the surface of this electrode, there will be some species getting reduced and some species getting oxidized. Both happen simultaneously and at equilibrium potential. The rate of species getting reduced and the rate of species getting oxidized is equal. And the current that we find out here is called as the exchange current density. Okay. There is no device that can actually practically measure the exchange current density at the electrode. So what we will do is plot a linear polarization curve on the potential side and then extrapolate the data to find out the exchange current density. Okay. On the potential side, you will have to plot a linear polarization curve. The plot should look somewhat like this. The x-axis is the log of current density and the y-axis is the potential. You will have to apply negative voltage with respect to OCP and a positive voltage with respect to OCP. Okay. So the curve will begin from here and then it will go at the positive range. 50 volts, 50 millivolts positive and 15 volt at the negative will have to make a tangent on this curve. And these lines at this point where it meets is the current density. So the third objective of this experiment is to generate a Tafel plot. For this, we will follow the equation over potential okay, so this is the Tafel equation wherein the y coordinate is the over potential and the x coordinate will be log of current density. For this, you will have to perform chronoamperometry. You will have to assume 4 over potential values and find the current density corresponding to those over potential. And this will have to generate for silver and platinum separately. After you find these 4 values, plot a graph. Y-axis should be the over potential, x-axis should be log of I. You will get these 4 points for let's say silver. You will have to fit a line which will pass through these points, and for platinum as well you will have to pass a line from these points, and the slope that you will get for this 2 graph is this B. The unit for B is millivolt per decade, which tells us the amount of over potential required to go from 10 milliamperes to 100 milliamperes per centimeter square. So basically the platinum, this will be the platinum and this is the silver. Platinum will require less over potential to go from 10 milliamperes to 100 milliamperes as compared to this silver electrode, which will be having more over potential than the platinum. I will show you how to construct the cell. There are 3 holes in the cap. One is for the reference electrode, this one is for the working electrode, and this one is for the counter electrode. Working electrode and the reference electrode should be close to each other. Insert the counter electrode from beneath and the counter electrode from above. Place all the electrodes inside the electrolyte and make sure that all the tip of those electrodes are immersed into the electrolyte. After this, Connect the reference electrode with the white cable, working electrode with the green one, and the red one is for the counter electrode. After that, you will have to open this program EC Prayog. In this, after you open, click on OK. Then you will need to connect the potentiostat with the software. Once it is connected, the device status will turn blue. After that, click on Experiment, TAFL. Here you will have to apply negative 250 millivolts with respect to OCP, and the final voltage will be 250 millivolts with respect to OCP. Scan rate is 1, step size is 1. Sample area, you will have to calculate the area of the wire electrode, assuming it is cylinder. Use the formula for cylinder. You will be given vernier caliper to calculate the thickness of this wire, and you will have to take the height of this wire equivalent to the amount of wire dipped into the electrolyte, and rest all values will remain as it is. Then you will have to select the path where the file will be saved. Click on these 3 dots, go to desktop, MM224, experiment number 2, select your section accordingly, and type roll number of one of your batchmate, and then press OK. After that, click OK, and the experiment will run. Initially the OCP is being calculated. Here is the status, and then there will be an equilibrium for 10 seconds. To change the scale on the X and Y axis, here is a drop down arrow for voltage. Go on voltage, format, and select decimals. For current, format and then decimals. After that, the current axis is logarithmic, so go on mapping mode, select logarithmic. This is ideally how the plot should look like. The voltage is on the x-axis and current is on the y-axis, but for calculation you will have to interchange the axis, and the plot should look like this. Point should come at this here, on this region, this way. And then you will calculate the current density by plotting the tangent. Yes. Okay, so now to calculate the tafel plot, you need to calculate the current density at different overpotentials. For this, you need to go to experiment, click on experiment, chronoamperometry. So you will first need to calculate the nust potential. Now let us assume that you have got nust potential as negative 1000 millivolt. Okay, so if you want your first overpotential to be 100, you will have to add 100 to this value, so it will be negative 1100 millivolts. Run it for 10 seconds, apply another 100 millivolts, so the new voltage applied will be 1200. Let it run for 10 seconds, add another 100 millivolts, will be negative 1300. Let it run for 10 seconds. Sample period is the time at which the data is being recorded. The current range is maximum 20 milliamperes. Initial delay is for calculating the OCP, which we actually don't need, so keep it at 1 second. Equilibrium time is 10 seconds. Then you need to select the path in which this file will be saved. Go to desktop, MM224, experiment 2, select your section accordingly, type your roll number, press OK. The status is seen over here. So the first over potential that we applied, the current corresponding here is seen over here. Okay, the second one is over here. Since we are continuously increasing the over potential, the current is continuously being increased. We have, I guess, three over potentials being set. So we have three values of current over here. You can use this value to then plot the tafel plot. Now you will see how to save this data. Right click on the plot, export data to clipboard, then open Word file, then paste. Here you have the data for this plot. Okay, then you can save this in the folder with the same roll number. Save. So the group who will be performing on AutoLab, there are 3 electrodes in this potentiostat. The red one is for working electrode, blue is for reference electrode, and the black one is for the counter electrode. Okay. So the blue electrode I am connecting with the saturated calamine electrode. And the black one is for the counter electrode, and the red one is for the working electrode. Okay, done. Go close. You'll have to open this software Nova 2.1. After you open it, go to Open Library. To calculate the current density, you will need linear polarization. Once you open this, go into AutoLab control and set the current range to maximum at 100 milliamperes. Don't move back and forth, keep it this way only. It will first calculate the OCP. OCP is it will run for 60 seconds. Then here you will have to set up the voltage range and make sure this is with respect to OCP. After, then click on options. Here also go and put it at 100 milliamperes. After that you click this triangle, it will start the electrochemical analysis. This box, this graph shows the calculation of OCP. This shows the change of potential with respect to time. Once the procedure is done, then click on this icon to save this file. In the format, select Excel, then export. Then on the desktop there is a folder MM224. Go to your section, save by one of your batchmates roll number and click save. Now I will show you how to calculate the current densities for the over potentials to calculate the tafel plot. Go on the software Nova 2.1, go to open library, then to chrono amperometry. Here go to AutoLab and then set the maximum current limit to 100 milliamperes. Then set the potential with respect to reference electrode. Now first you need to calculate the nust potential. Let us now assume that you have got negative 1 volt. So if you want to apply an over potential of 100 millivolts, then it will be negative 1.1 volt. Okay, then go to record signals, record it for say 10 to 20 seconds. I will put here 10 seconds. Then again you will be needing to calculate the current density for 3 to 4 different over potentials. So set another one, maybe you are putting 200 millivolts. So put 1.2 volts over here. Record signal will be 10 seconds. Now let us have an over potential of 300 millivolts. So I will set here negative 1.3. Record signal for 10 seconds. Go to record signals and make sure the current limit is set to 100 milliamperes. After everything is done, click on this triangle button to start the process. Here is the graph, current versus time. The first over potential is being applied and the corresponding current is being recorded over here. Since we are continuously keeping on increasing the over potential, so the second over potential the current increases. These are absolute values. You need to divide it with the surface area of the electrode to get the current density. So these are the 3 values that we got. To save these values, click on this icon, then go over here, select the file format to Excel and then export. On desktop MM224, go to your section and save it by one of your batchmates roll number and click save. Done.